Hello everyone. Thank you for giving me the opportunity to present the light-only liquid xenon experiment on behalf of the LOLAX collaboration. Firstly, I'd like to give you talk about the motivation of the LOLAX experiment. In the current stage, LOLAX is supplementary to the UNCSO experiment, which is designed to search the neutrino-less double beta decay. Well, the neutrino-less double beta decay, if it ever exists, is predicted to be an extremely rare event, which means the discovery of such events requires a high energy resolution to reject the background source. And although the silicon photon modifier has been chosen for the photon detection, some of the questions regarding its performance has remained open. For example, whether the performance of the silicon photon modifier will be stable in a long-term operation within the liquid xenon. And some of the intrinsic properties of the silicon PM will sabotage the energy resolution. For example, we would always have the axonal crosstalk within the silicon PM. And those axonal crosstalk would increase the number of photons detected. That would causing the spectrum to shift. So those questions are what the LOLAX is trying to answer. Well, for the next phase, the upgrade of the LOLAX focuses on increasing the time resolution from the current nanosecond to 100 picoseconds, or even at the end to 10 picoseconds if the digital silicon PM can be successfully installed. With the upgraded time resolution, we can successfully separate the Schwarzkopf and scintillation light for detailed studies. We also want to answer how much of the scintillation photons come from the direct xenon excitations, not the recombinations. If we can successfully achieve the 10 picosecond resolution, we would like to use that to study the time of flight in the gamma detections. That could contribute to the positron emission tomography.
What are the basic concepts? Well, there are 24 silicon photon multipliers installed to cover a large range of the solid angle. We also intend to use different optical filters to separate the Schwarzkopf and scintillation light. The radioactive source was placed on the tip of a needle, inserted to the center of the LOLAX chambers. Here's some details of the filters. As you can see from this plot, the Schwarzkopf spectrum centered at around 170 nanoseconds, while the spectrum of Schwarzkopf light span a large range of wavelengths. We use bandpass filters, which centered at 175 nanoseconds with 20 transmittance to select the scintillation light, by using a long pass filters, which allow the light greater than 225 nanoseconds to pass. Because the intensity of the scintillation is predicted to be much higher than that of the Schwarzkopf light, the 22 of the silicon PM were covered with this long pass filters for the Schwarzkopf light. Only one silicon PM was chosen for the scintillation light. And the last silicon PM was left without any filters, so it can observe all different kinds of light. Here's the current silicon PM used in LOLAX experiment, the Hamamatsu UVU4, which has a high efficiency at ultraviolet range covering the scintillation light. Each of the silicon PM contains 4 multiple pixel photon counter, the MPPC. Each of the MPPC contains 14,000 pixels, which can operate individually in gig mode, capable of a single photon counting. Here's an example of those pixelated structure taken by a microscope. The advantage of having those pixels allow the silicon PM to detect multiple photons at different positions simultaneously. This is an example of the charge distribution. Those peaks represent a different number of photons detected in one single pulse. Our analysis also shows there is a good linearity between the charge of those peaks and the number of photon-electron equivalents. Here are some pictures taken during the installation of the LOLEX system. The first one is the LOLEX chamber, which is 3D printed. As you can see, we have 4 silicon PM installed at the bottom and another 4 on the top. The rest are on the side. Here's a simplified version of DAQ systems, which neglect a lot of details. For each individual MPPC, there is a feed-through cable that gives us 96 cables going to the amplifier. We sum the signals from the individual segments, which covered with long-pass filters. So at the end of the digitizer, there are 30 channels. The current digitizer we use have a sampling rate of 16 nanoseconds, and that time is the main restrictions on our current time resolution. Let's look at some of the analysis results from the last liquid Xenon operation. This plot is the charge spectrum of the bare channels. So most of the light seen by the bare channel is supposed to be the scintillation light. As you can see, there are 2 components here. They corresponding to the 2 beta decays we expected in our experiment. That's from strontium to yttrium and yttrium to zirconium. And we compare this result with the simulation. They are only partially in agreement. And one of the key factors in the simulation is the detection efficiency. And the value for this simulation is only 5%, which is lower than the 12% expected value. This simulation is a preliminary one. We are developing this simulation model and try to find out the reason behind this disagreement. We also checked the correlations between the bare channel and the long pass channel. What we expect to see is the scintillation light plus the shrink of light from the bare channels against the shrink of light from the long pass channels, just like what is demonstrated in this simulation plot. But our data shows the long pass channel observed about 20 times more light than what we can expect from the simulation. So why such a large discrepancy? Here are some explanations we come up with. First, we are going to check whether the filters works as expected. As you may recall from the transmission spectrum in the previous slide, there are actually a very large errors for the transmission near the region where the transmission is close to 0. And also those numbers was measured in vacuums. So what is exactly is the value for them in the liquid Xenon is still unknown. And another possibility is the fluorescence from some of the material, for example, the cage or some of from the filters. We can examine that by studying the time structure, as the fluorescence have a large time scale compared to the scintillation and shrink of light. And another explanation is whether the axonal crosstalk act as a wavelength shifter. This we will explain in details in the following slide. Another explanation is the detection efficiency. We know that this efficiency varies for different wavelengths, but how much difference did play in our measurement is under investigation. At the end, we even though it's very unlikely, but we are also going to check some whether we overlook some of the physics. For example, whether the shrink-off yield is actually higher than what we expected, or whether there are some another source of scintillation light beyond this long-pass filter region. Okay, let's check the possibilities of the axonal crosstalk as the major wavelength shifters. Well, the axonal crosstalk is caused by the photon emitted in avalanche. Based on the study done by my colleague John at China, the spectrum of those secondary photons is mainly in the infrared range. So both the bare cyclones and the cyclones with long pass filters are sensitive to the axonal crosstalk. Based on the SAM studies, the crosstalk photon yield is less than 1 per avalanche. And if you look at the Hammermaster datasheet, the detection efficiency for those photons is about 10%. So if we neglect all the other factors like the solid angle or the reflectivity, the possibility of the axonal crosstalk as a long pass channel should be less than 10%. This number shows that the axonal crosstalk is unlikely to be the major contribution to our unexpected light seen in the long pass channels. So here's the future plan for the Lolex experiment. First, we are going to upgrade the DAQ to get this time resolution upgraded. It's probably going to happen later of this year. And after that, we probably going to replace part of the Hamamatsu silicon PM with the SBK UVU HD3. It's because the SBK silicon PM shows better stabilities in some of the tests, and it is also likely to be the one which is going to be used in the experiment. We also plan for a long-term stability test some times in the future. In the far future, we still plan to replace the silicon PM by the photon to digital converter to see whether we can actually achieve this 10 picosecond time resolution. To conclude what we have achieved for the Lolex experiment, first, in the last operation, we achieved the stable liquid Xenon operation. And the analysis of the data shows excellent photon electron equivalent resolution. We have a good observation of the strontium-19 spectrum. The simulation is only partially in agreement with the observation, and the reason is under investigation. We also find that the long pass channels actually see much more light than we expected, and this is the pressing issue that we are trying to solve. The future analysis will focus on timing studies, hopefully with the new data taken with this upgraded time resolution. That's the end of my talk. Thank you for your attention. Please do not hesitate to raise your hand for questions. Thank you.